Hello and welcome to the Elvatech channel. Today we are going to explore a critical topic for aerospace industry, XRF analysis or X-ray fluorescence. In aerospace, where precision and reliability are key, XRF technology plays a vital role in ensuring the quality and safety of materials. Aerospace components are exposed to extreme conditions, from high temperatures to intense mechanical stress. This means the materials used in aircraft and spacecraft need to meet the highest standard of quality. XRF analysis helps ensure that the metals and alloys used in the components are exactly what they should be, free of harmful impurities. In this video, we will take a closer look at how XRF analysis supports the aerospace industry by providing fast, accurate, and non-destructing analysis. XRF analysis offers several key advantages for the aerospace industry. First and foremost is the non-destructive method. This means that the materials being tested remains intact, which is especially important when dealing with the high-value components or parts in limited quantity. Another major benefit is the high accuracy of XRF analysis. It can precisely detect and measure elements in metals and alloys, ensuring that the material composition is exactly as specified. This level of accuracy is crucial in aerospace, where even the smallest variation in material composition could lead to failure under stress. XRF is also incredibly fast. In just a few seconds, you get the detailed results that show the full elemental composition of the material. This saves valuable time in production and quality control, eliminating the need for long lab processes and allowing for on-the-spot decisions. So, with XRF, you get non-destructive, fast, and highly accurate analysis, making it an essential tool for ensuring the reliability and safety of aerospace components. XRF analysis is widely used in various stages of aerospace industry, from material selection to quality control. One of the key applications is the analysis of alloys and metals used in aircraft and spacecraft components. For example, airspace-grade alloy, such as aluminum and titanium, must meet strict standards for strength, durability, and corrosion resistance. XRF can quickly determine if these alloys contain the correct amount of key elements, such as chromium, nickel, and molybdenum, which are critical for their performance. Another application is in detecting trace amounts of harmful impurities. Even small amounts of elements like sulfur or phosphorus can lead to premature corrosion or weakening of the material. XRF allows engineers to identify and eliminate these impurities before they cause any problem. XRF is also used to monitor protective coating applied to critical components. Whether it's a thermal barrier or an anti-corrosion coating, XRF can measure the thickness and composition of the coatings to ensure they meet aerospace specifications. In this industry, meeting international standards is not just a recommendation, it's a requirement. XRF analysis plays a crucial role in ensuring compliance with strict regulations like ISO standard and AS9120, which govern the quality measurement system for aerospace manufacturing. These standards require that every material used in aircraft and spacecraft manufacturing is tested and verified. XRF provides the precision needed to meet these requirements, giving manufacturers confidence that their materials are compliant. By using XRF spectrometers, manufacturers can ensure that every batch of material is within the required specification for chemical composition. This helps prevent potential risks, such as structural failure, and ensuring the safety and reliability of critical components. Whether it's verifying the composition of an alloy or checking the quality of protective coating, XRF gives manufacturers a powerful tool for meeting the highest aerospace standards. Let's look at some real-world examples of how XRF is used in the aerospace industry. One of the most common applications is in the production of turbine blades. These blades operate under extreme conditions, and even minor variation in the alloy composition can affect their performance and durability. XRF analysis is used to verify the exact composition of nickel-based superalloys, which are critical for ensuring the blades can withstand high temperatures and mechanical stress. Manufacturers use XRF to confirm that every batch of material meets the necessary standards before the blades are installed in engines. Another example is in production of lightweight aluminum and titanium components for aircraft. These materials are chosen for their strength-to-weight ratio, but their performance depends highly on the correct alloy composition. XRF is used to check for the presence of key elements like chromium and vanadium, ensuring that materials can handle the stress of flight. In addition to production, XRF is also used for maintenance and repairs. During inspections, XRF helps detect any degradation or contamination of materials, ensuring that aging components still meet safety standards. These examples highlight how XRF analysis helps maintaining the high standards required in aerospace industry, contributing to the overall reliability and safety of aircraft and spacecraft. In conclusion, XRF analysis is an essential tool for aerospace industry. Its ability to provide fast, accurate, and non-destructive testing make it invaluable for ensuring the safety and reliability of materials used in aircraft and spacecraft. Whether you are analyzing high-performance alloy, checking for impurities, or verifying the thickness of protective coating, XRF helps ensure that every component meets the strict standards required in aerospace. It's a critical technology that supports the industry's commitment to safety and innovation. So, let's start our practical part of our video. And today we will analyze 3 samples of the special Elvatech sample box. Right, we have a lot of them here, but we will use just 3 of components that uses most in aerospace industry. We will take in aluminum, as it's like really light metal. Also, we will take chromium nickelum. It has the chromium nickelum base. Both elements are also used widely in aerospace industry and building. And also, for sure, we will take the titanium. It has titanium aluminum alloy in it, but actually both these elements are widely used for construction of spaceships. So let's start basically with aluminum, as we selected first. And this is actually the lightest metals we have right now. All that we need to do is from the sample box, we just need to turn upside down this metal, and we can measure it from this side where nothing actually printed on. So we have our device ready. All we need to do is just to select the right calibration. Here we will use the calibration for alloys with the detection range from magnesium to uranium. So we will be able to extend our analysis results, and let's position the device right on the sample, and let's start the analysis first. Oh, and actually we just forget to select the duration of our analysis, because usually in experiments we are doing just a fast screening to show you the overall picture of the analysis. And here we will do the same. We will stick to the same. We will set 5 seconds, but for further and more deeper analysis of the alloys, you can take from 15 to 25 seconds, just to make sure that everything is compliant and reliable. So we set it for 5 seconds. Let's start our first analysis. Alright, so we have our first result, and actually this was the aluminum 99.3, and but the actual composition of aluminum in this sample usually set on 99.6, so it's averaging. And we have the results where the aluminum is a base alloy, the leading alloy absolutely in this sample, and it contains 99.67% of aluminum in this sample. Also, we have a bit of ferrum, the iron, basically a bit of magnesium, we have some zinc, we have copper, and all other elements are like really with a small concentration, so we will not even name it. But basically, even the fast screening showed us the appropriate concentration of aluminum in this sample. Right, let's move forward. This we will take apart for now, and let's try to measure our second sample. It was chromium nickelus base. So we got it. Just again, we need to turn it upside down. This absolutely clear and clean surface. Position our device and making a second analysis. Alright, so we are done with our second analysis, and even a fast screening showed us like really pretty close and almost similar data here. So we have the leading element, the base element of this sample is actually ferrum in concentration of 96.8, and the appropriate concentration for this sample is actually 96.2 ferrum. Also, we have a nickel, which actually has the concentration of 1.42, so it's almost 1.5%. But here we have actually the position of 1.42, and the averaging position for it is 1.4. So here we absolutely good too. And also we got the chromium that consists of a little bit lower than just 1. It has the 0.75, and actually the appropriate data for this sample is 0.76, so we was really cool with 100s almost. Alright, we are done with the second one, and let's move on to our titanium aluminum sample, and it will be really interesting to see the contamination of elements in this one. So we have the sample here. It says titanium aluminum. And again, we will turn it upside down, measure from this side of the metal. Let's position it. And again, also in-built camera showing us that we positioned it right, and the surface is absolutely attracted to analysis fully. And now starting the analysis itself. Alright, so we finally have the results of our third and last for today's sample, and looking for data we received just in 5 seconds, we can say that it's really close to the average in data for this alloy. So let's take a closer look. Well, leading element, as was expected, it was titanium in concentration of 88.7, and the actually average in concentration for this element is 88.5. With the appropriate error of 0.4. So we absolutely fit in this range, and if you set for more time, like for 15 or 20 seconds, you definitely will receive the right proportion of this element in this sample. Well, next we have aluminum in concentration of 6.1, just a little bit over 6, and appropriate data for this element is 6. So we also fit in here. And also we have the vanadium here with the concentration of 4.8 with the acceptable error of 0.3%. And the actually appropriate data for this element is 5%. So here we actually fit absolutely cool. Again, as with our previous two samples. So as you can see, and as we can conclude for our today's experiment, With the cert samples, same as with previous two samples, we had the really clear data even with the fast screening. And if you will set your device for appropriate time, for example for 15 or 20 seconds, you will receive really accurate and reliable data that you can understand your materials could be used, or you should refuse to build something from them. And basically it will give you the clear structure and understanding of the any kind of supplier and his materials. So as you just saw, using the XRF technology in building and creating the Aerospace craft is really crucial and also very important. It helps to determine if this material can be used further in production process, or it better to refuse it straight away and change the supplier. If you would like to learn more about how our analyzers can help your business meet these challenges, feel free to reach out straight to us. We are always here to provide expert advice and support. Thank you for watching. Don't forget to subscribe to our channel for more informative content, and give this video a thumbs up if you found it helpful. Stay tuned and see you soon. Bye.